Welcome back. This is COT 3100. Today's topic is about the growth of a function. For example, whenever we see a function, let's say x squared plus x plus 5, we want to know how fast this function can grow in the size. Okay, and sometimes this is extremely important in computer science because we need to figure out how fast, for example, if you're assigning, let's say, a passports to every employee, what model should we use, what polynomial should we use, and how we should assign, and we need to be able to figure out how fast this is going to grow and what's going to be the upper limit or lower limit, and we want to have some idea that how fast a function could grow. And there are three notations that we use, and one is a big O notation, and the other one is a big omega and big theta notation. And in this section, I'm more interested in you understanding the terminology and what it means and how we use them. And I'm not going to emphasize on the very much detail of it because it is kind of outside the scope of the course. And because we're going to use this in number theory and counting, which we are going to discuss it later on in this semester after this part. Those are the two chapters that we are very much interested because we use those material in our telecommunication courses and software engineering courses. We use them in database courses, and we need to understand those. And sometimes we use these notations to explain, especially in number theory, how this numbering system works. And so that's the reason we want to discuss this topic. One of the frontiers, or the latest, basically, the person that came up with some of these notations, especially omega and theta notation, was the Donald Knuth, who is the professor at Stanford University, and he is still teaching there, even though with very old age. The growth of a function, whenever we come up with an algorithm, for example, and we want to understand, we really want to understand that how the size of the problem, if an algorithm, we come up usually with the algorithm to solve a problem, all right? Now, if the number of inputs to that algorithm as increases, we want to know how fast that solution also is going to increase. So basically, as we see here, we have a number of inputs, and then number of the solutions to that problem can increase. And we want to understand how these two can grow and how they are related to each other. And also we can compare, for example, the efficiency of two different algorithms for solving the same problem. All right, this algorithm works much more efficient, much more in the size smaller to solve this problem than using the other methodology or algorithm to solve the same problem. We can also, as I explained before, determine whether it is practical to use a particular algorithm as the input grows. Sometimes the input grows so fast, and the solutions, it grows much faster, and then that may not be the right way of, that algorithm may not be the right way of solving the problem. Because once they grow so fast, they use the memory so much, and which causes problem in terms of the once you fill up the memory, basically your computer is going to crash, or it's not going to produce the desired output. Two of the areas of the mathematics where questions about the growth of functions are studied are, one is the number theory, which is in chapter 4, which we're going to discuss next, and then also combinatorics that we may not get to study those, but in number theory, the growth of functions, it's very important that how the number theory works and what it is. And that's why we are going to look at this big O notation. Big O notation means what? Means definition is, we read the definition exactly from the book, so there will be no confusion. It says, let f and g be two functions, all right, from the set of integers. Each one is function of a set of integers, or the set of real numbers, doesn't matter, to the set of real numbers, both of them. F is a function of set of real numbers or integers, and g is the function of set of numbers, real or integers. We say that f of x is big O of, okay, this is read, f of x is big O of g of x if there are constants c and k such that f of x, the absolute value of it, is smaller than or equal to c times g of x, all right, whenever x is greater than k, which we're going to look at it, all right. Let's take a look. Here's the f of x. F of x is this function, and c times g of x is this function, and then we have a value k here, which we say x, when x is greater than k. When x is greater than k, you see the f of x is smaller than c times g of x. So we say the growth of f of x, all right, is the big O of, O meaning order, big O of g of x for two different values, for when x is greater than k and for a special value c. And the part of the graph of f of x that satisfies f of x smaller than c times g of x is shown in color, which is this one. What is the significant about this part? It is when x is greater than k, right? Because for k smaller than, for x smaller than x, f of x is bigger than g of x. If one pair of witnesses, those two numbers, let me go back, those two numbers, c, what value c should be, and k are called witnesses, all right? So f of x is big order of g of x if, all right, if f of x is smaller than c times g of x. And then we say f of x is big order of g of x because if you look over here, g of x is this. When you multiply by c, it becomes this one. We say f of x is big order of c times g of x if x is greater than k. And there is a value c that if you multiply by g of x, that becomes, this relationship becomes true, meaning f of x is now, for x greater than k, is smaller than c times g of x. In that case, we say f of x growth, it really is in the order of c times g of x. I will look at an example and we understand it easily. Let me go here. Example, show that f of x is equal to x squared plus 2x plus 1. All right, we look over here. What is the order? What is the growth rate of the f of x? Really the growth rate of the f of x, or basically we could say the f of x is big O of x squared, because it all depends on the x squared, how fast x squared, when the value of x goes up, x squared is a number much bigger than 2x plus 1, right? So the order that it is going to, this polynomial is going to grow is really depends on the value of x, or it depends on the value of this terminology right here, x squared. So we say f of x is the big O of x squared. X squared we consider as g of x, right? G of x is x squared. So, and you can see that when x is greater than 1, this is your basically k, and x is smaller than x squared, and 1 is smaller than x squared, then we can prove that one, that x squared plus 2x plus 1 is smaller than or equal to, you put, you change every one of these x's here, or lack of x's, with the x squared, the same terminology, and this becomes 4x squared. So x squared plus 2x plus 1, it is smaller than 4x squared. So we see that f of x is smaller than c times g of x. G of x here is x squared, and c is k, c is 4 in this case. All right, and so we look at this one and we say, okay, f of x order of squared. Now, in general, keep in mind, anytime you see any polynomial like this, anything, x6 plus 2x5 plus 2x3 plus 2x4, and you go all the way down, any polynomial in this format, the highest degree that you find out, you say that polynomial is in the order of that. That is the rule. So you need to know that one. So here's the f of x is big O of x squared. Alternatively, when x is greater than 2, we have 2x smaller than equal x squared, and 1 is smaller than x squared. Hence, 3x squared. So we try to figure out what's this value of c and k, and which is true for both of them in this case. And let's take a look over here. So you notice that for x greater than 1 or equal to 1, x squared plus 2x plus 1, which is this one, which is your f of x, is smaller than for x squared. Therefore, this one, f of x, is in the order of x squared, or it is big O of g of x, which is x squared. Both f of x and g of x, called x squared, are such that f of x is big O of g of x, and g of x is big O of f of x, but for the different value of the k, and c and k. We will look at these two functions. If they are both in the order of each other, then we will say there are a different way of discussing those, because they have the same order. They are in the same order. If f of x is a big O of g of x and h of x is larger than g of x, that means g of x is smaller than h of x, then we could say for all that f of x is big O of h of x, because here we're saying that g of x is the big O of h of x, and f of x is big O of g of x, then f of x is big O of h of x. And let me see. For example, show that 7x squared is big O of x cubed. Well, when x is greater than 7, all right, this is the c, x squared less than x cubed. Take c is equal 1 and k is equal 7 as witnesses to establish that 7x squared would c equal k work. We'll have to put them in the format to see if we can prove this one. Show that n square is not order of n. It is not, because n square is in the order of, well, if it is, let's see. Suppose that there are constants c and k for which n square is less than c times n. All right? And that's what we want to prove. We want to prove that f of x is smaller than c times g of x. Here, we're saying g of x is n, correct? Then we're saying if this one is smaller than or equal to C of n. Whenever n is greater than k, then by dividing both sides of n squared by C of n, by n, then n is smaller than or equal C must hold for all n greater than k. Contradiction. Sometimes it doesn't prove. And this also, if you try to solve this one, you will see that, oh, 7x squared is not really order of x cubed, and it is much smaller. Now, let's look at a big function in general, the polynomials that I discussed. Anytime you see a function like this, a polynomial like this, a sub n times x to the power of n, then this all the way till down, and also the thing is that the assumption is that a sub n is not a zero. It's a sub n is not a zero. There will be always a number. In that case, we say the highest degree will be the order of the f of x. So f of x is order of x to the power of n. How do we prove this one? Well, here it says that we put the absolute value. What's this value of that one? And we put the other side right here. And what we are doing here, this should be a0, by the way. So this is a0, it's a typo. And we say f of x is smaller than or equal to, okay, smaller than or equal to, and we add the absolute value of the coefficients a sub n minus 1, right? We separate those, and then we factor out x sub n. X sub n comes out, this becomes a sub n plus a sub n minus 1. You basically, when you factor it out, x sub n, you're taking that much out of that one. So what is left? Xn minus xn minus 1, it's left with x, right? All the way till this becomes x sub n. And then here you have x sub n, and then you have this, basically the c up here. This is your value of the c. F of x is smaller than or equal to c of g of x, right? This is c and x sub n. Take c is equal to this one, right? And k is equal 1, then f of x is order of x n squared. So always, when you see the polynomial, the highest power that you have, that function is order of that one. In other words, the leading term, a n x to the power of n of a polynomial, dominates its growth. Because its growth, when you graph this one, you will see its growth really primarily dependent on x to the power of n. All right. There are a few functions that I want to show you here that are important. Use big O notation to estimate the sum of the first n positive integers. What are the first positive integers? 1 plus 2, 1 plus 3, first n positive integers, all the way plus n, right? Now, you write this one down, and then you say, well, this is, if I replace every one of these terms with n, this is clearly smaller than this one, right? And this, if you have n times n, you're adding up, that's almost n squared. Then we say, all right, 1 plus 2 plus this n is order of n squared, taking c is equal 1 and k is equal 1. The other one is the n factorial. F of n is equal n factorial. N factorial means 1 times, 2 times, 3 times, 4 times, all the way times to n, right? So like, for example, 4 factorial means 1 times 2 times 3 times 4. And so we write that down. N factorial is this, and then we replace every one of these with n. So how many n's do you have? N times n, that would be n to the power of n. So n factorial is order of n to the power of n. And here is another one. Use big O notation to estimate log of n. Given that n factorial is smaller than n factorial, previous slide, then log of n factorial will be smaller than n times log of n. Because what happened, we said n factorial, if you remember in the previous one, n factorial was order of n to the power of n, correct? So n to the power of n, based on logarithmic factor, that this power comes here is equal same as the n times log of n. Log of n factor is smaller than less than n times log of n. Hence, log of n factor is order of n log of n, taking c is equal 1 and k is equal 1. All right. And here are the display of some of these functions that we just showed. N factorial grows much faster. And for example, if you want to put in 20 factorial in your calculator, it wouldn't give you a number because the number is so huge. Or 2 to the power of n, then n squared, n log of n log of n. And here's just the 1, straight line. There's no x, right? And as you see, the behavior of functions as n gets larger or x gets larger. Instead of n, you could say x. But as you see, now if you had an e function, f of x is equal to e, then that would have gone way up like that, and it would have grown much faster than n factorial. All right, this is not you take a look at it. It's not that it's the same stuff that we discussed, but in a different order. It's showing to you what are the sizes of each functions, why they're bigger. Now, big omega notation. Now, if you remember in the big O notation, we said f of x has to be smaller than or equal to c times g of x. Basically, I defined the upper limit for the growth of a function of f of x, right? Big omega notation defines the lower limit of the growth of a function, at least how much a function grows. And that's called big omega notation. Let f and g be functions from the set of integers or the set of real numbers to the set of real numbers. We say that f of x is big omega of g of x if there are constants in case such that f of x, instead of saying smaller than, this time saying if they are greater than or equal c times g of x. That's the only difference. That is called big omega notation. That's all you need to know. For example, here we say f of x is 8x cubed plus 5x squared plus 7 is big omega of g of x. G of x is what? X cubed, where g of x is x cubed, right? This one. It is all dependent on we said anytime is a polynomial, it all depends the order, the growth of that function or polynomial depends on this term. Now, f of x is x7 is greater than or equal to 8 times x cubed, which it is, because it is at least 5x squared plus 7 greater than that for all positive real numbers. So in this case, we say that g of x, x squared, then is basically we are saying f of x is smaller than, or f of x is bigger than or equal to cg of x. So, or we can turn it around. We say that means g of x is smaller than f of x. So we say g of x is x cubed is order of x, 8x3 order of the f of x, and f of x is 8 times x cubed plus 5x squared plus 7. So f of x is smaller than g of x, we say f of x is big O of g of x. If f of x is greater than g of x, we say f of x is a big O of g of x, or we say now that g of x is smaller than f of x, then we say, or g of x is big O of f of x. Theta notation is, which is this one right here. Let f and g be functions from the set of integers or the set of real numbers to the set of real numbers. The function f of x is big theta of g of x if f of x is big O of g of x, and f of x also is big omega of g of x. If f of x is also big order of f of x and also big omega of theta g of x, then we say f of x is big theta of g of x. We say that f is big theta of g of x, and also that f of x is of order g of x, and also that f of x and g of x are of the same order. It means they both are in the same order because f of x is big order of f of g of x, and also g of x is big order of the big O of the f of x. That therefore, we say that is the big theta. F of x is big theta of g of x if and only if there exists constants c1, c2, and k such that c1 of g of x is smaller than f of x, but f of x is smaller than c2 of g of x. So there are two numbers. For one number, f of x is smaller, but another number, f of x is greater. In that case, we say f of x is big theta of g of x. All right, these are some proofs here. Let me show you this. This is very important that you need to know that. If f of n is equal to 1 plus 2 plus 3 plus 4 plus 5, all the way plus n, right? What is the value of this one? Value of this one, it is proven that I don't want to go through the proof right now, it's 2 times n minus 1 divided by n. All right? That is what it is. Now what we have already shown that f of n is order of n squared in previous problems. Now we need to show that f of n is also big omega of n squared, we need a positive constant c such that f of n is greater than c n squared. Right? If f of n is smaller than c n squared is your g of x. Then you say that's a big order of, or big O of that. If it is greater than, we say that is big omega. For sufficiently large n, summing only the terms greater than n over 2, we obtain the inequality. This should be greater than this one, right? For all the terms that are greater than n over 2, we obtain the inequality. And if we say 1, we assume the 1 is n over 2, and then this would be n over 2 plus 1, and we keep going always all the way up to n, and then that comes to, we simplify that one, comes to n squared over 4. Taking c is equal to 4, f of n is greater than c n squared for all positive integers n. Hence f of n is big omega of n squared, and we can conclude that f of n is big theta of n squared because already we know it is f of it's a big order, big O of g of x, and since we showed that it is also big omega of g of x, therefore it is big theta of the g of x. And these are some other notations, that examples that you could take a look. And complexity of algorithms is another discussions that I'm going to discuss a little bit about it, and not in this. I want to end this section, and then in the next lecture I want to discuss complexity of algorithms very shortly. How do we define complexity of an algorithm? And usually we define them in terms of time or memory usage. How complex an algorithm is in order to solve a problem. The reason we have the algorithm is step-by-step instructions to solve a problem. how complex it is. In the old days, we looked at the C program, for example. We said how many if-then statements we have, how many of these statements we have. Then we counted those. We said, oh, this is the complexity. This number is the complexity of this algorithm. But today we use these notations and we come up with a better way of explaining it. And all we're going to have to do in that, just explain what it means, the complexity, and that's all we're going to discuss it. Then we're going to move on to the next chapter 4, which is the number theory. All right, let me stop at this point. I'll see you next lecture.